Okay, second lab in Module 9. I'm not going to lie, this one is a lot of work. Having said that, it's pretty interesting stuff, so I hope you get a lot out of it anyway. 2 tasks. The first one is a comparative watershed study. The second task is a channel change detection analysis, where you'll be subtracting 2 DEMs to determine a DEM of difference. Okay, so the premise for the first task is a comparative watershed study. I'm not sure if you're familiar with Hubbard Brook Experimental Forest, but this is a place where they have done very extensive paired watershed studies. They use a control watershed and then perform treatments on very similar watersheds and alter the landscape to determine how these treatments affect the way the watershed reacts. You're going to be doing the same kind of thing. Basically, a group of scientists, they have a control watershed, and they're asking you to analyze some surface characteristics of this watershed landscape to determine if the slope, aspect, and curvature meet the requirements for a paired watershed study. So as a little bit of a refresher, just remember that there are different surfaces, different rasters that we can create from DEMs. You're going to be creating a slope, aspect, and hillshade in addition to curvature surfaces in this lab. If we start with a DEM, remember slope is calculated from the adjacent cells. So for any given operational cell, slope is the maximum slope from the adjacent cells, and the maximum slope is the output value for the operational cell. Slope can be calculated in degrees or in percent rise, and it's important to just make note of this when you're running slope. You need to choose the correct units. The range in values, if you run slope in degrees, is from 0 to 90. So if you think about a 45-degree angle, when you're running it in degrees, as you approach vertical, you approach 90. But when you run slope and percent rise is rise over run multiplied by 100. So if you have a 45-degree angle, your rise over run is 1, so a 45-degree angle slope is a 100% slope. As you approach vertical, you approach infinity. Your range of values when you run slope and percent is 0 to infinity. This is just an example of slope output. If you look at these classifications for slope, we have a value range from 0 to just over 510. So what are the units? This is percent, not degrees. If this were run in degree slope, it would be 0 to 90, or something close to 90. Okay, aspect should always look like this. If you ever run aspect on a DEM and you do not get a result that looks like this, something's gone wrong and you should rerun it. It automatically outputs a default classification system that's very unique in that it's circular. Aspect values are the compass directions, so north is represented by both the highest values and the lowest values. So again, if you don't get this result when you run aspect, just run it again and keep trying until you get something that looks like this. There could be something wrong with your input DEM, or you're running it on something else like slope or something like that. Always run aspect on the original DEM. The aspect calculates the direction of the steepest slope, and the output, like I said, is the direction that that slope is facing. Okay, hillshade is both the most awesome thing ever and the bane of my existence. So hillshade is an awesome visualization tool. It represents the brightness of the surface. But the cell values don't mean anything except for what color gray they are. So in a grayscale color ramp, there's 255 different bins of color, and these numbers represent those colors, the bin number. So hillshade is a fantastic visualization tool, and we use it all the time, but it should never be included on your legend because the values don't have any significance for your audience. You can alter 2 things when you're running hillshade, altitude and azimuth, and we're talking about the light source when we're talking about these things. The altitude is the angle of the sun in the sky, the theoretical sun. This is a good thing to change, especially when you're dealing with flat landscapes. If you think about the sun being directly overhead, it really flattens shadows and you get a lot of flattening on the surface. But if you bring the sun down close to the horizon, that's when you get really exaggerated shadows, and that's a very helpful way to make your terrain pop a little bit. The azimuth is the direction of the sun along the horizon relative to north, and this is something I would recommend that you never mess with. Our eyes are used to seeing things illuminated from a certain angle. If you change the azimuth of the illumination source, sometimes your peaks look like valleys and your hillshade gets inverted. Alright, so just remember, hillshade is not the same thing as elevation. It's not the same thing as slope. It's not hill slope. So again, the range of values simply represent the color on a grayscale color ramp. And I'm just beating this into your head because I hate seeing hillshade on legends on maps. So use hillshade on your map, absolutely. It looks fantastic. Even the Hoff agrees. Good looking. But hillshade on your legend has no significance and no meaning. Don't do it. Leave it off your legend. Okay, you will also be creating a curvature surface. Curvature is the second derivative of the surface, or the slope of the slope. So we can calculate curvature two ways. Profile curvature is the direction of the slope. Planform curvature is normal to the slope. When we talk about profile curvature, we're talking about acceleration or deceleration as you cross the cell in the downslope direction. A profile curvature of 0 means there's no change in the slope as you cross the cell. So a negative value is an acceleration. A positive value of profile curvature is a deceleration. In planform curvature, we're talking about how water diverges or converges as you go down the cell slope. So a positive value of planform curvature would lead to water diverging across that cell. And a negative value means water is converging as you cross that cell. And again, a 0 value means there's no change in slope. This is just an example of how planform has been presented by students in the past. I really love the idea of using an inset map to show some detail here. I think you could zoom in more here to show the differences between profile and planform curvature. All right, zonal statistics. This should be a review. You did this in Lab 7 as well. Just remember that you can calculate zonal statistics either as a shapefile, where you pick one statistic, or as a table where you can calculate multiple statistics for your zone. And this is what you're going to want to do again because we're asking you to report both the mean and standard deviation for the different metrics. You can produce a table, present your results if that's easier for you. The second task is to create a DEM of difference. So this is a way of doing some change detection analysis. You're going to be working with two very high quality manually surveyed DEMs. One from, I think, 2010 and one from 2011. I could be off, but a really high grade survey of a stream channel was done in 2 different years. And what you can do is simply subtract the old DEM from the new DEM to produce a DEM of difference that shows the change in channel over time. So we're looking at being able to map erosion and deposition within the stream network. To do this, one small detail you're going to need to just realize that you're doing as you work through this process is determining an error threshold. So we have our 2 different vertical measurements of elevation in time 1 and time 2. But in collecting these surfaces and doing these surveys, there is a certain amount of error that we can account for and quantify. I do recommend looking at the PDF if you're interested in learning more about this process. I've included a link to a PowerPoint by Dr. Joseph Wheaton, who has created this tool. What you need to do is apply a minimum level of detection threshold. And like I said, this PowerPoint kind of walks through this threshold process and where these errors come from. But you can see here, as you do apply a different threshold, you cut out the maximum peaks in the histogram, but you're cutting out a lot of that error and trying to account for the error in creating these vertical surfaces. So, yeah, that's pretty much it. I know I didn't go through that very carefully, but there's a lot of information on the web about it, and I do include a link if you want to take a look at that PowerPoint. So you're going to be submitting 2 formal maps for this lab, both exported to PDF. The first one is a result of the watershed comparative study. So you're going to be showing at least 4 data frames, 1 for each surface calculation that you did, and then reporting the statistics for each metric. You want to include the mean and standard deviation for slope, aspect, planform, and profile curvature. You'll also be calculating the total area of the watershed that has a slope of greater than 45 degrees and calculating the total area of the watershed that has southern exposure. The second map is just a very simple illustration of your DEM of difference that you created. You will have to import the symbology to get a proper legend for that one, but that second task should be pretty quick. Okay, that's it.